So we have a warped or curved spacetime. Particles have inertia. What does it mean, particles have inertia? It means that there's an inertial field on space plus time. What is this inertial field? We know it's a worldline curvature, connection curvature field equal to gm over r squared. Right? And that is the straightest possible geodesic line in spacetime. So just like a particle moves with a constant speed in a constant direction and you accept that, well, that's inertia, particles accelerate. When you look at it in the wrong frame, you're looking at the source frame, they seem to accelerate. Yes, why? Because really what they're doing is inertial motion, gravity inertia motion. Their world line is geodesic of that curved spacetime. Okay. So again, for all intents and purposes, as far as we're concerned, when you're in free fall, you're in an inertial state. When you're not in free fall and you're fighting gravity, you are in a non-inertial state. Therefore, the straightest world lines are world lines of free fall particles. And again, that tells us something weird about space plus time, because we know that the geometry of space plus time is such that the straightest possible lines in it are what to us look like curved lines. Another way of interpreting this, and with this we kind of jump into general relativity, is to say, instead of having curved world lines in this diagram and somehow saying that's the straightest line, which is kind of absurd, we have to recognize that space plus time has weird properties, it's warped, and we would have to draw the axis in some strange warped way to represent reality. And when we did that, we would kind of stretch out this line. Instead of being curved, it would suddenly become a straight line, or the straightest possible line. It's only because we're drawing the axes like this, which is illegitimate for representing this warped spacetime, that we get a curved line. So because we're uncurving this curve by warping our axis, we can consider the warping to be curvature. We're giving curvature to space plus time. And in the appropriate axis for a curved space plus time, what otherwise would have been a curved line becomes straight, or straightest. Where can you see an analogy of this? I showed slides last time of the globe, the Earth, right? If you fly from Europe to New York, you might fly over Newfoundland, Labrador, right? If you look at a map, it's flying like this on a flat map. Why is that? It's actually not, if you look on a globe and you draw the line, you'll see it's a great circle. Maybe you've learned that a great circle is the shortest distance between 2 points on a sphere. All right? If you took a sphere, if you took the map of the Earth on a sphere and you cut it off, you pulled it, you peeled it like an orange peel off the sphere, and then you tried to flatten it, you can't. You have to cut it like a petal of a flower in order to get the shape to be flat. And then you have all kinds of strange things like, you know, countries split in half, and one part of the country is here, another part of the country is on the other petal near it, and the other, and so on. You have a distortion. When you look at a regular map, which is continuous, the distances and the geometrical relationships are distorted. They're not accurate, because they've arbitrarily kind of, well, not arbitrarily, but they flattened out what actually is a spherical surface. So the true geometry can only be determined when you look at the globe. So now we're going to go and try to find a field theory, basically a field equation for this world line curvature, which in the more sophisticated version we'll say is some kind of curvature of the space-time.